Hi students, good morning. Welcome back to our physics classes. Let us start with our new semester, the third semester, with a new chapter. So we have stopped with the chapter heat transfer. Today we are going to start with our 19th chapter, that is thermodynamics. So as the name indicates, thermodynamics, the term comes from two different concepts in physics, that is temperature and dynamics, thermodynamics. Temperature something related to the heat, and dynamics something related to the changes. So thermodynamics actually deals with what heat energy can do with a system. That means whenever heat is transferred into or from a system, what changes may occur in that system, that is dealt in this thermodynamics. That means effect of heat in a system, that is dealt in thermodynamics. So as an preface to this thermodynamics, we have talked about the chapter heat transfer. That means how heat can be transferred from one region to another, and what are the basic criteria for supply heat into a system, how or from where to where heat can be flow. All these matters, we can say a hint can be derived from the last chapter, heat transfer. So in that chapter we have seen that heat energy can be transferred from a higher temperature region to lower temperature region spontaneously. What do you mean by spontaneously? That means without any initiation, heat can flow from a high temperature region to a lower temperature region. High temperature region to lower temperature region. So what is actually heat? What is actually heat? Heat is a form of energy. It is a form of energy. When you are talking about the system, I already told you, whenever you consider a particular system, effect of heat is more easily can be measured within a gaseous system, because in gaseous system the particles are in random motion. There is no attractive force between the particles. So when you are considering a gaseous system, or when you are supplying heat energy to a gaseous system, it can be easily visible. The effect of heat in that system can be easily visible. Or at the same time, if you are removing heat from a gaseous system, its effect can be easily visible. So effect of heat energy is more visible or easily visible in gaseous system. So during all our discussions throughout, in the coming chapters, coming topics also, we are considering a gaseous system. We are considering gaseous systems. Okay, so you keep in your mind that whenever you consider a thermodynamical system, it's a gaseous system. And moreover, that gaseous system should be an ideal gas. So what is ideal gas? You know, ideal gas equation PV is equal to nRT. So a gas which can obey that equation, we will come to that. Means later we will talk about the properties of gaseous system. So we will discuss it in detail. But when you are dealing with these thermodynamical systems, you remember that it's an ideal gas. Thermodynamical system means it is an ideal gas. Okay. So when you are considering an ideal gas, it has its particles there. So the total energy of all the particles present in the system, that is measured as heat energy. Total energy of all the particles present in the system, that is measured as the heat energy. And these two terms you have to learn, or these two terms you have to talk in related, that are heat and temperature. So what is the difference between heat and temperature? Heat is, as I already told you, heat is a total energy of all the particles present in the system. And temperature is a measure of hotness. Temperature is the measure of hotness, which means it is the average kinetic energy of a single particle within the system. Average kinetic energy of a single particle within that system. Which means whenever you are supplying heat energy into a system, what will happen to the average kinetic energy of the particles? Automatically it increases. Which means as the heat energy is supplied to a system, its temperature increases. Can you relate it? And when you are removing heat from a system, what about the kinetic energy of the particles? Obviously it will decrease. Which means its temperature also falls. So kinetic energy, average kinetic energy of a single particle within a system, that is temperature, and the total energy of all the particles present in the system, that is heat energy, that is heat and temperature. So when you consider a thermodynamical system, and when you are supplying heat energy into a system, its temperature rises, and whenever you are removing heat from that, its temperature falls. So when you are entering into the term thermodynamics, we have to be sure about some terms related to that. That is a system, what is a system, and what is the surroundings, what is an isolated system, what is a thermodynamical system, and what are the thermodynamical variables and equation of a state and thermal equilibrium. So we are trying to find out the definitions for all these terms that I have already told you. That is a system, surroundings, then thermodynamical system, how you can define a thermodynamical system, what are the thermodynamical state, and what are the thermodynamical variables, then what do you mean by thermal equilibrium. So all these we are trying to find out the definitions of all these terms through this chapter. It's a basic chapter for thermodynamics. We can start with the first term, that means system. What do you mean by a system? A system means the part of the universe. We are thinking in that wide range, a part of the universe that you are isolated for your studies. System means a part of the universe that you have isolated for your studies. That means you are concerned about the changes happening in that region only. That is system. The rest of the universe is called surroundings. Rest of the universe is called surroundings. Except that system is called surroundings. What is an isolated system? There is no relation between system and its surroundings. There is no relation between, there is no interaction between, there is no transfer of anything between the system and its surroundings. Then that system can be considered as an isolated system. That can be considered an isolated system. Then what do you mean by a thermodynamical system? The system in which heat can find some effect, that can be considered as thermodynamical system. Then when you are considering a thermodynamical system, we can say that the thermodynamical system is under a particular state. What do you mean by a thermodynamical state? Which means to define thermodynamical state, you have to define thermodynamic variables. Which means whenever you have a thermodynamical system at a particular state, it should possess constant values for some of its properties. What are these properties? These properties are PVTs. It's PVT. It's not private limited. It says pressure, volume and temperature. Pressure, volume and temperature. That are the PVTs. Pressure, volume and temperature. So for a thermodynamical system, it has a particular value of pressure, volume and temperature, and it is a constant, and we can say that that system is under a particular thermodynamical state. That system is under a particular thermodynamical state. If any one of these changes, then we can say that it is changing from one state to another. That we can call a thermodynamic process. That is known as a thermodynamic process. So thermodynamic process happens when any one of these three changes, then the system is changing from the state from one to another. That process is called thermodynamic process. So these are called thermodynamical variables. These are called thermodynamical variables. Or it is also known as the state variables. It is also known as state variables. Why they called state variables? Because thermodynamical system of a state, thermodynamical state of a system is perfectly defined with the values of these PVTs. If any one of it is changing, thermodynamical state is also changing. That is why these three are called thermodynamic variables or the state variables. So these are the basic terms that you have to keep in your mind while we are going through this concept of thermodynamics. Okay, so that is PVTs, pressure, volume and temperature. which are the state variables, which are thermodynamical variables. If any one of these is changing, the system changes its state from one to another. That is a thermodynamic process. Okay, so that are the basic of thermodynamic system and thermodynamics. Okay. So we have defined heat energy of a system, or generally heat energy. So heat energy is the total energy of all the particles present in that. Total energy means a particle can have different kinds of energy, different forms of energy. Means kinetic energy, it can possess potential energy, then vibration energy, translational energy, different kinds of energy particles in the system can have. So the sum total of all these energies is known as the total heat energy of the system. Okay, means sum of all kinds of energy possessed by all the particles present in the system. That is, but we can't say that all kinds of energy is possessed by all the particles in the system. That is different. Anyhow, total energy of all the particles present in the system is known as heat. How you can increase the temperature of a system? And I already told you, when you are supplying heat energy to a system, its temperature rises. And temperature is a measure of heat. A temperature is a measure of heat. If the temperature of a system is high, which means its heat content is more. And if the temperature of a system is less, means its heat content is very less. That is the importance of temperature in a thermodynamical system. Okay, so we have said that there is a term in thermal equilibrium. There is a term thermal equilibrium. What do you mean by thermal equilibrium? Suppose you are having two systems A and B. We are having two systems A and B. Thermodynamical system. You know what I meant by the thermodynamical system. So when there is no heat transfer between A and B, there is no heat transfer between A and B, then what you can infer, I already told you, we have already seen that heat can be transferred only from a high temperature region to low temperature region. That means there should be a thermal inequilibrium. That means the temperature should be different for two systems for making a heat transfer between those two. So since we are saying that both are having the same temperature, there is no temperature difference, which means there is no heat transfer between A and B. Simply we can say that if there is no heat transfer between two systems, we can say that those two are at the same temperature. If there is no heat transfer between two systems, we can say that both are at the same temperature. So thermal equilibrium is an interesting term. Thermal equilibrium is an interesting term. Why I say this interesting means this thermal equilibrium, the term is given by, or it is evolved from a thermodynamical law. And the name for that thermodynamical law is very interesting. That is zeroth law of thermodynamical system, or zeroth law of thermodynamics. Zeroth law. Can you imagine that zeroth law? First law, second law, okay. So what do you mean by zeroth law? Zeroth law says that if three systems are there, first of all I define the zeroth law, then I will come to its name. So zeroth law says that if three systems are there, A, B, C, A is in thermal equilibrium with C, B is in thermal equilibrium with C, then A and B are at the same temperature. That is the definition for temperature given on those days. If A and C are in thermal equilibrium, B and C are in thermal equilibrium, then A and B are at the same temperature. Automatically, it comes to the concept that A, B, C are at the same temperature. That is known as thermal equilibrium. That is the thermal equilibrium. So, definition of temperature is given by zeroth law in this way. That is, if A is in thermal equilibrium with C and B is in thermal equilibrium with C, and the temperature of A and B is same. Actually, this should be the first law of thermodynamics. This should be the first law of thermodynamics. But before coming to this thermal equilibrium, the concept of thermal equilibrium, we found that, I mean, not we, the scientists found that there are heat transfer between the systems, and the system, different systems are doing some work. Then we are having some useful work at the, I mean, at the expense of heat energy. All these matters were found, and they formulated first law of thermodynamics already. But that heat transfer and all will be valid only when you are defining thermal equilibrium. But the concept came late. Then first law of thermodynamics is already established, so we can't come in change the name of that first law. So this is the law before first law. This is the law that should be, that's supposed to be defined before that statement, which is already known as the first law. That is why law before the first law is defined as the zeroth law. Interesting, no? So zeroth law says that if A and the C are in thermal equilibrium, B and C are in thermal equilibrium, then A and B are at the same temperature. Okay, so that is zeroth law of thermodynamics, and we are talking about our heat transfer. So how you can increase the temperature of a system? You can increase the temperature of a system by supplying heat energy. Suppose when you are considering your just your hands, how you can keep it warm? Warm means increase the temperature. So you can increase the temperature while, when suppose your burner is on and you can keep the hand above that burner, automatically its temperature will rise. Is it? And the same you can do by rubbing your hands. And when you are rubbing the hands for 1 or 2 minutes and after you are touching it, you can feel that it is warmer. What is the difference there? In the first case, what happens if, or you are dipping your hand into a bucket full of hot water. After removing, you can see the hand is also heated. That means temperature raised. So you can increase the temperature of a system by 2 ways. One is directly you can supply heat energy into that. Second one, you can do a work on that. That work can be converted into energy. That depends upon, means already our work energy theorem says that work done on a system will store as its potential energy or change in kinetic energy. Now I am saying it can be transferred in the form of heat energy also. Suppose you are having a iron rod and you are beating that with a hammer. After 2 or 3 hits, when you are touching it, it is getting heated. Is it? So you are not supplying heat energy directly into that, but you are doing a work on that. That work is transferred into energy. So there is a relation between work and energy. There is a relation between work and energy. So work is a form of energy. Work is a form of energy. How you can convert work into heat energy, or how you can convert work into equivalent heat energy, or energy into equivalent work. So that is known as W is equal to, we can have an equation, W is equal to J into Q. W is equal to J into Q, where J is known as Joule's constant. J is known as Joule's constant. And you know, initially work is measured in joules and energy is measured in calories. Energy is, remember, Q is heat energy. Q means we are representing heat energy with the Q. Rate of heat is H, that we have already seen. H is equal to Q by T. H is equal to Q by T. That is heat energy, that is rate of heat. Differences, that means different notations we can find that only. So W is equal to J into Q, where W is the work and Q is the heat and J is the Joule's constant. Joule's constant. And W work is measured in joules and Q is measured in calories. Energy is measured in calories. Okay, so W is work and Q is heat. W is measured in joule and Q is measured in calorie. So Q calories of energy is equal to W amount of joules. Q amount of calories you can convert into W amount of joules. So we can say that W is equal to 4.2 Q. W is equal to 4.2 Q, and W is measured in joule and the Q is measured in calories. So we can say that 1 calorie is equal to 4.2 joules. 1 calorie is equal to 4.2 joules. Okay, so that conversion factor you are already knowing, that is how you can convert joule into calories or calorie into joule. So if 4.2 joule of work is done, on a system, its heat energy increases by 1 kilocalorie. When 4.2 joule amount of work is done on a system, its energy increases by 1 kilocalorie. Okay, I mean 4.2 joule of work is done on a system, its energy increased by 1 calorie, not 1 kilocalorie. That is 4.2 into 10 to the power 3 joule of work is done, then its energy increases by 1 kilocalorie. So when we are converting directly, 4.2 joule of work is done on a system, its energy increases by 1 calorie. That is why we are saying that W is equal to 4.2 Q. That is 1 calorie is equal to 4.2 joules. So remember that 1 calorie is equal to 4.2 joules or 1000 calories. 1000 calories is 1 kilocalorie. 1 kilocalorie is equal to 4.2 or 4200 joules. This conversion factor you are already remembering. Okay, so that is the conversion factor or converting heat into energy. That is the process by or the conversion factor W is equal to 4.2 Q, which means 1 calorie is equal to 4.2 joules. 1 calorie is equal to 4.2 joules. Okay. So that is the conversion of heat into work and work into heat. There is a relation between work and heat and work. Okay, then we can say that three terms are related to a thermodynamic system. These are heat, work and internal energy. Heat, work and internal energy. Suppose you are supplying heat into a system, or suppose you are doing a work on a system, its heat energy increases. Or if a system does some work, its heat content decreases. But we can't say that if you are supplying heat energy to a system, the total heat is converting into equivalent amount of work. When you are considering the work and heat supplied to a system and the work given by that system, we can't say that Q equal to W. It's an ideal condition only. Some amount of heat energy is losing, but there is no another chance of losing that heat energy, but it is not converting into equivalent amount of energy. So equivalent amount of work. Then what happened there? What happens there? Which means whenever heat is supplied to a system, a part of that heat energy is stored within that system. And the remaining part is converting into equivalent amount of work. A part of it is stored within the system and remaining part, most of the part is, that depends upon the nature of the system. But automatically when you are considering a system from which we require a work done, with the expense of heat, most probably all amount of, not whole, maximum amount of energy is converting into useful work, but some amount is not converting into equivalent amount of work, but it is stored within the system. That amount of energy stored within the system is known as internal energy. That is known as the internal energy. So internal energy of the system depends upon the state of the system. That means whenever the system remains in the same state, its internal energy also remains same. If the internal energy, if the system changes its state from one to another, then only its internal energy changes. Otherwise, what happens is, when you are supplying heat into a system, keeping the state same, it can do a work. Then its internal energy remains the same. But I already told you that is an ideal condition. Whenever a system is supplied with some amount of energy, it can do some work. The same time its temperature rises. When the temperature rises, state changes. When the state changes, internal energy changes. So we can say that internal energy change you can sense by changing temperature. If the temperature remains same, internal energy remains the same. It happens when isothermal processes are happening. We can't say that always it is an ideal condition, but at the same time you can talk about the work done, what is happening there to the work done. That happens. So whenever heat is given to a system, if the if the temperature of the system changes, we can say that its internal energy also changed. Which means change in internal energy can easily sense by or easily measured by changing temperature. Okay, so here we have defined some terms related to thermodynamics. So what is a thermodynamical system? What is its surroundings? Then what do you mean by state of a system? Then state variables, how you can change the state variables, and what is the thermodynamical process? Then zeroth law, heat, temperature, then relation between heat and temperature. Remember, 4.2 joule of work is equivalent to 1 calorie of heat. 4.2 joule of work is equal to 1 calorie of heat. So 1 joule is equal to 4.2 calories. So 1 calorie is equal to 4.2 joules. 4.2 joule of work is equal to 1 calorie. So 1 calorie of heat. So 1 calorie is equal to 4.2 joules. Okay. So all these matters we have discussed now, and that's all for today. And we will meet in the next class.